So let's first look at what we did in lecture number 20. So in lecture number 20 we did quantum measurements, and specifically the projective measurements. There are two other kinds of measurements, but we mostly looked at projective measurements. So for a given operator A, measurement operator always corresponds to some dynamical variable. So for that operator A, if it acts on a state, then the system in that state collapses into one of the eigenstate of the system in the basis of the measurement operator, and one obtains the eigenvalue A, and the probability of this collapse is given by the mod square of the projection of the state on the basis vector or the eigenk. The probability PAI, that is of the collapse, that a measurement of the observable yields the result AI. Then we saw that it can be written as this psi and this pi I operator psi, and this pi I is what's called the projection operator. We also saw specifically we saw that if we, using this projection operator, if we act this on the state, then of course it yields the particular eigenket. So this pi, there can be n such projection operator for an n dimensional system, and a pi I projector basically yields the eigenket AI. And of course sum of all these projection operators is equal to 1. And if it's if this is for the discrete system, discrete basis, but if it's a continuous variable operator, then this completeness relation reads as xx. This is for the position basis, so that's just an integral here. The operator itself can be represented in terms of these projectors in this manner. So A is AI, that's the eigenvalue, and the projectors, and this is sum over these from I equal to 1 to n if it's an n dimensional basis, and for a continuous variable operator then it's just an integral in this manner. So whenever we talk about measurement, then we also looked at, whenever we talk about measurement, this is always associated with the measurement device. For example, we saw that polarization is associated with polarization in horizontal vertical basis is associated with the polarizing beam splitter in the horizontal vertical basis that splits a light field based on its polarization in the horizontal and vertical directions. And similarly, like a lens is a measurement device. Lens along with the CCD camera can be measurement device for a momentum. A CCD camera itself can be measurement device for position and so on. So now one of the aims of quantum measurement is to be able to find or predict or reconstruct the quantum state, unknown quantum state. But if one knows that the incoming quantum state is in one of the eigenstates, then only one measurement is needed to guess or reconstruct the state in any basis. So we actually saw this explicitly for the polarization basis, but this is true in general, that if the system is known to be in one of the eigenstate of the measurement operator, then only one measurement is required to reconstruct the state. But of course, if the system is in a superposition state, then one requires an infinite number of measurements to actually reconstruct the whole state. Okay, so this was quantum measurement. Now let's get to EPR paradox. So let's get started with quantum entanglement. I have shown this slide earlier as well. So this is a popular interpretation of quantum entanglement, that if there are two entangled particles, and if we disturb one, both of them actually get disturbed. This is actually not absolutely correct, but I like to show this because this kind of conveys the idea in a much simpler manner. But we will see in this the concept of entanglement in a much more mathematically rigorous way. But this very idea of entanglement, this was not really liked by Einstein, Podolsky, Rosen, to be specific, and they basically objected to this kind of phenomenon. And in this lecture, we will actually look at and go through the exact arguments that they provided in order to kind of argue as to what was wrong with this very concept of entanglement. In fact, what was wrong with the very quantum theory itself. So this was the paper that Einstein, Podolsky and Rosen, they published in 1935. This is a very famous paper. And basically in this lecture I'm going to follow the exact formalism of this paper. And this paper, in fact this is the title of the paper, that can the quantum mechanical description of physical reality be considered complete. So here they are basically questioning the completeness of quantum theory. And of course, as I pointed out, this is also kind of referred to as EPR paradox. But essentially in this work, they question the very completeness of quantum theory. So we will go through the exact arguments, but here are the few statements taken directly from this paper that gives a kind of overall view of what they were thinking of quantum mechanics at the time. So they say that if this is just quoting EPR from this paper, if without in any way disturbing a system, we can predict with certainty, that is with probability equal to unity, the value of a physical quantity, then there exists an element of physical reality corresponding to this physical quantity. So here they are basically referring to the fact that measurements should be certain, that one should be able to predict something with equal probability, and if that is the case, then only we can say that there exists an element of physical reality. Essentially they are questioning, they are defining what should be the idea of physical reality, what should be the requirement for something to be physically real. Then they say that in a complete theory there is an element corresponding to each element of reality. A sufficient condition for the reality of a physical quantity is the possibility of predicting it with certainty without disturbing the system. So here they are defining what should be the element of reality, and for that their main argument is that for reality one has to be able to predict it with certainty without disturbing the system, and disturbing the system should not be kind of a part of that definition. Then finally they argue that in quantum mechanics, in the case of two physical quantities described by non-commuting operators, the knowledge of one precludes the knowledge of the other. Here they refer to the fact that we have for non-commuting operators we have uncertain relation, in the sense that if we know one very precisely, the other one cannot be known with arbitrary accuracy. So then they say, then either one, the description of reality given by the wave function in quantum mechanics is not complete, or two, these two quantities cannot have simultaneous reality. Consideration of the problem of making predictions concerning a system on the basis of measurements made on another system that had previously interacted with it leads to the result that if one is false, then two is also false. One is thus led to conclude that the description of reality as given by a wave function is not complete. Well, I will not go through this here. I just wanted to kind of point out, these statements from the paper. But we'll go through the paper now and through the maths to see what they are actually referring here, what they actually mean here. But one point is clear, which is what I wanted to kind of bring out here. They were sort of feeling, and they were actually concluding, that the quantum theory as given in terms of wave function is not a complete theory, and they thought that something more needs to be done with the theory. Maybe some additional variables needs to be supplied to make it a complete theory. So now we will go through the math and arguments again, what they have done in this paper to explain what they are pointing out here. Okay, so let's suppose we have a one particle system in an eigenstate AI of some measurement operator A, corresponding to some physically observable quantity. Then we know that if A, the operator, acts on AI, which is the eigenket, then we just get the eigenket with eigenvalue AI. So the system remains unchanged, and further action of the A, the operator, on this state yields the same value AI, because this is eigenket, so the state doesn't change. So then we can say that there is an element of physical reality corresponding to A. Now this definition is coming from the arguments given, or the definition given by Einstein, Podolsky, Rosen in the very beginning of the paper. So this situation in quantum mechanics, they identify that yes, in this case we can say that there is an element of physical reality corresponding to A, because operator A acting on this state yields a value AI, and if we just repeat the measurement we get the same value. And then one could have predicted this with certainty even without this A actually acted on this one. Okay, now let's take a concrete example. So let's consider a one particle system in one of the momentum eigenket For example, we can call it psi p naught. And as a physical example, we can see a photon in a plane wave, a particle in a plane wave, and with momentum p naught and plane wave, that can be that is a system in the momentum eigengate. Now, such a momentum eigengate in the position basis can find by taking the projection on the position basis, and we know then this is given by this plane wave function. It is the I p naught x by h bar, where p naught is a number and that is the momentum of the one particle system. The momentum operator in the position basis, we know it is given by, this is basic quantum mechanics we are just doing here. Momentum operator in the position basis is minus I h bar del x, and we know that the action of the momentum operator on the momentum eigengate p acting on psi p naught is that the state remains the same and we get the p naught out as the eigenvalue. Of course, this is in the state form. If you write in the wave function form, it is minus I h bar del x acting on psi p naught x, where psi p naught x is this, and so we get p naught out, I by h bar p naught out, and then so it's p naught psi p naught x. So this is just getting the momentum value out. Okay, so what we see that for a system in one of the momentum eigengates, there is an element of physical reality associated with momentum. Why? Because without even disturbing the system, we could have predicted that we will get the momentum of the momentum value of p naught, and that making a measurement doesn't change this value, and there is no uncertainty about this as to what value we would actually get, and that's why there is an element of physical reality associated with momentum for this particular system, which is a one particle system in the momentum eigengate, that is a plane wave. Now, for such a system, what about the position? Now, we know that for momentum eigengate, if we act on it with a position operator, this is not of the form of an eigenvalue equation. That means we won't get psi p naught and times a number. But we know that in this case, what we can ask is basically the position probability. We can ask what is the probability that the particle is found between position x1 and x2. And this, we know that this can be obtained by using this position probability density integrated over x from x1 to x2, and psi p naught x is as this form. So take the mod square is just 1, so that's just 1, so x1 x2 dx, that's x2 minus x1. So the probability, so I mean an action of a position operator, this tells us here that position is not fixed. All we can find is the position probability, and the position probability between x1 and x2, that is the probability that the particle is found between position x1 and x2 is just x2 minus x1. This essentially says the particle is equally likely to be found anywhere. So this one particle system in one of the momentum eigengate has fixed momentum, but its position is completely uncertain. That means it is equally likely to be found at any position. Okay. Now let's take another example, and this time we consider a particle in a position eigengate. As an example, we can see a wave diffracting from a point, and that this is the x direction, and that's the point x naught from where this wave is coming. So now, I mean, this is physically realizable example of a kind of position eigengate. Now, position eigengate in the position basis, to a very good approximation, we can write that as a delta function, delta x minus x naught. And action of the position operator on this wave function is that since this is a position eigengate, we of course get the same state, and this x naught, that is the value, eigenvalue that we get out. So in this case, the system being in one of the position eigengate, there is an element of physical reality associated with position. And when we say element of physical reality, this is as according to Einstein-Podolsky, according to the definitions by Einstein-Podolsky and Rosen. So now in this case, what about momentum? Of course, if we act upon the momentum operator on this position eigengate, then of course we do not get it like this. So this equation doesn't have any meaning. So all we can say is that the momentum is not fixed, but then the question is, what is the probability that the particle is found to have momentum values between p1 and p2? And again, we can do the same math. So the probability that the particle has momentum between p1 and p2 is just the momentum wave function, that is whole square, that is the momentum probability density, and integrated from p1 to p2. So what is psi x naught p? Well, psi x naught p we can calculate because we know the wave function in the position basis. So knowing the wave function in the position basis, we take the Fourier transform, and then we can get the position wave function in the momentum basis. Since the wave function in the position basis is a delta function, that we can just put in here, and that gives us that the wave function in the momentum basis corresponding to this wave function is e to the minus I p x naught by h bar. So if we just take the absolute square of it, this is essentially 1, and so that's why this quantity is p1 p2 dp, that is p2 minus p1. So again we have here this particle is equally likely to have any momentum. So a particle that is in a position I can get with this wave function, its position is fixed, and that is at x0, but the system or the particle is equally likely to have any momentum value. Okay, so what we have done so far is that for a wave, for this example where we have a system in a position eigenket, position is fixed and momentum is completely uncertain. This we can write as delta x, that is the uncertainty in x, that is equal to 0, because position is of course fixed, but the uncertainty in p, that is the momentum, is infinity. Similarly, for our plane wave example, the momentum is fixed and position is completely uncertain. That means the uncertainty in p is 0 and the uncertainty in x is infinite. But this was just one set of example, but in general we know that in quantum mechanics we have delta x times delta p is greater than h bar by 2, and this is called the Heisenberg uncertainty relation. This basically says that two non-commuting operators such as position and momentum, and if they don't commute, for example x and p not equal to 0, for such a case they cannot be simultaneously measured with arbitrary accuracy. The position and momentum, these cannot be measured with arbitrary accuracy. If we know one very accurately, then our knowledge of the other one will not be as accurate. Of course, these two are extreme examples where in this case we know x very accurately, and so we just don't know anything about p. In this example we know p very accurately, and hence we know nothing about the position, as it can be anywhere. Here the measurement accuracies are dictated by the uncertainty relation, and in other words we can also say that the two non-commuting operators cannot have simultaneous physical reality. That is, a system cannot simultaneously be in the eigenstates of two non-commuting operators, because if it is in the eigenstate of position, then of course delta x is 0, and if it's in the eigenstate of momentum, then of course delta p is 0. So system cannot simultaneously be in the eigenstate of two non-commuting operators. So this is all standard quantum mechanics, this uncertainty principle in this form and with this interpretation is the very first principle of quantum mechanics. Okay, now Einstein, Podolsky and Rosen, they basically took this very first principle, and then using this first principle they actually saw an apparent contradiction within the quantum theory, and that's what we will actually describe now. So for this, let's consider a system of two entangled particles. These particles had a common past, that means they interacted in the past, and then but after that they separated, and now they are space-like, the present is space-like separated. So now there is no interaction after they have separated. So they can be any wave function, but let's assume that this is the wave function considered by EPR in this paper. So they assume they just take a wave function for this two particle system in this form, in the position basis. So psi x1 x2 is psi p x2 up x1 dp. This is for the first particle, and this is for the second particle. So that's the wave function corresponding to first particle, that's the wave function corresponding to the second particle. So we see that this is a continuous superposition of two particle states. So this two particle state is a continuous superposition of such two particle states. And upon measurement, if we actually go and measure it, we'll find, and this is what we did in the last lecture on quantum measurement. So this is a superposition of many such state defined by this index p here. And so if you make a measurement, we'll find just one of these terms, psi p x2 up x1. So we will find, upon measurement, we won't find this entire integral, we'll just find the state or system to be in one of the superposition state. And so the thing is, now if you find the first particle to be in upx, then the second particle is guaranteed to be in psi p x2. So this state is fixed by this index p. Of course, if you find the first particle to be with up prime x1, then the second one is guaranteed to be in psi p prime x2, as it is an integral over p. Okay, so this is a generic wave function. Let's make it more precise. So for that, they actually consider this wave function. So for psi p x2, they consider it to be in this form, and up x1 they consider to be in this form. Now, what is this wave function? This we have just done a few slides ago. This is a wave function. This is essentially an eigenfunction of this e to the minus ip x2 minus x1. Of course, we can take any form for these wave function, but EPR took this form because this is the simplest and conveys the main idea. So for this one, we see that this is an eigenfunction of the momentum operator of the second particle, that is P2, and this we can see that this minus IH bar del x2, if we just act on it, we get minus P out and this stays. So this is an eigenfunction of the momentum operator of the second particle. What about this? This is actually an eigenfunction of the momentum operator of the first particle, and the momentum operator is given by minus IH bar del x1. So we can see if we operate minus IH bar del x1 on this one, we get P out and the state. So this is an eigenfunction of the momentum operator of the second particle, and it gives the momentum minus P. This is an eigenfunction of the momentum operator of the first particle with eigenvalue P. This one is minus P, this one is P. So we can write this state for this particular example. We can write the state like this, and the interpretation that we have is that, of course, this is an integral over P. That is a summation, that is superposition is given in the form of the integral. And of course, if you make a measurement, then as we discuss here, it has to be, this two particle system will collapse into one of these states that are part of this superposition. So if you make a measurement, if you measure the first particle and find it to be in the momentum eigenstate up x1 with momentum p, then the second particle is guaranteed to be in the momentum eigenstate psi p x2 with momentum minus p. So what we find is that, of course, each particle can have any momentum value, but if you find the first particle to be with momentum p, then the second one is guaranteed to have momentum minus p. Okay, so that's the situation. Now what we do is let's write this state. Right now this one is in the momentum basis, and with this particular example. Now let's write this state which is in the momentum basis in the position basis. For that, this e to the minus ip x2 minus x naught by h bar, that is the wave function for the second particle. Let's write it like this. So we're just writing e to the minus ip x2 minus x naught as an integral over x, and that's the delta function comes here. We can check if we just integrate over this delta function goes away, and we can replace this x by x2 minus x naught. Similarly, this e to the ip x1 by h bar, that can be written as an integral over this dx prime in this manner. Okay, so now that we have written this integral like this, we combine the terms containing p. So one from here, one from there. So it's e to the minus ip x minus x bar, x minus x prime. Oh, this should be divided by h bar dp, and then we have these two delta functions. Now e to the minus ip x minus x prime, that actually gives us an integrate of minus infinity to infinity. This actually gives us a delta function x minus x prime. So we have three delta function and two integrals over dx and dx prime. We integrate over dx prime, and then we obtain this one, so which is a product of two Dirac delta function. So the same state which in the momentum basis has this kind of representation, the same state in the position has this kind of representation. Now when this has this kind of representation, this again corresponds to, this is the wave function corresponding to particle number 2, and this is the wave function corresponding to particle number 1. We can also call it psi, this one we can call it as a phi x x2, and this one we can call it as vx x1. Now what is this delta x minus x2 plus x naught? Now this delta x minus x2 plus x naught is essentially the eigenfunction of the position operator of the second particle with the eigenvalue x plus x naught. This again we had seen when we were discussing the position eigenket. And this delta x1 minus x, this is essentially the eigenfunction of the position operator of the first particle with eigenvalue x. These are the two eigenfunctions we get. Again, this is an integral over dx. That means this state we are representing as a superposition over this x. But of course, when we make a measurement, the system will collapse into one of the terms in the superposition. And as a result, we'll see that of course we can get any x value, but once we make a measurement and if we find the first particle to be in the position eigenstate Vx x1 with position x, then the second one is guaranteed to be in the position eigenstate with eigenvalue x plus x naught. So again, upon measurement, any x value is possible from negative infinity to infinity, but if the first one has a position, if the first one is measured to be at position x, then the second one is guaranteed to be at position x plus x naught. Okay, so what we have here is that we have for the same wave function, so for the same system, we find that if we make a measurement of the momentum of the first particle, and if we find that momentum to be p, then the second particle is found to be with momentum minus p. But if we decide to look at the position of the first particle and then we find that its position is x, then the position of the second particle is found to be x plus x naught. Of course, this minus p, this is a momentum eigenstate, this is state with x plus x naught this is the position eigengate. So it seems that by our choice of measurement is deciding whether the state of the particle here is a momentum eigengate or a position eigengate. So in other sense, we can also say that if once we make the measurement of the momentum here p, then the momentum of the second particle is fixed. But if we decide to make a position measurement, then the position of the second particle is fixed. So what we here have is this conditional uncertainty on the particle, on the second particle based on the measurement already done on first, times the conditional momentum uncertainty of the second particle based on the measurement already done on the first particle. This can, at least in this example, it can actually be 0. So that means this product can actually be less than or equal to h bar by 2, which is the Heisenberg uncertainty relation. So this was the feature they pointed out, that for such a wave function, which is definitely allowed within quantum mechanics, we have this interpretation. This is in contradiction to what we saw for the very first principle of quantum mechanics, that is the Heisenberg uncertainty relation. So EPR then interpreted this as well. These are the facts that actually come out when we construct these functions and see what happens upon measurement. So they basically concluded that yes, we find that the second particle can either be in the momentum eigenstate or be in the position eigenstate depending on the measurement performed on the first particle. So a measurement on the first particle decides whether the second particle will be in the position eigengate or in the momentum eigengate. And here we need to note that the particles, once they have separated, there is no interaction between them. There is no other measurement or disturbance that this particle has seen. It is just that a measurement on this particle is deciding whether this particle is in position eigengate or in momentum eigengate. But according to the first principle of quantum mechanics, a particle cannot simultaneously be in the eigenstates of both position and momentum. So of course this particle cannot be in the simultaneous eigenstate. So it seems that a measurement here, the choice of the measurement is kind of collapsing this particle into either position or momentum eigenstate, which is in apparent contradiction with the first principle of quantum mechanics. And this fact, this apparent contradiction, this is referred to as EPR paradox. So that was the gist of that paper and their argument that I had in the very first slide. So with these observations, basically then the question that if this is the feature that we see within quantum mechanics, that the first principle says that one cannot have a particle or a system cannot have cannot simultaneously have the two eigengates. But if we consider a two particle system, then we do have a situation where we find that a measurement performed on the first particle collapses the system into either one eigengate or in the second eigengate of two non-commuting operators. And the only way this can be explained is perhaps by saying that this particle probably exists or probably has the simultaneous eigengates, which is again in contradiction with the first principle. So with these observations, basically the question is quantum mechanics really complete? And if it is, or maybe it is complete, but it requires some additional hidden variables to properly explain the measurement results. So this was the essence of EPR, and in fact in the next lecture, there was an effort known as the hidden variable interpretation of quantum mechanics, in which a new theory was tried and the attempt was to supplement quantum mechanics with some hidden variable and see if one can get rid of these features of quantum mechanics. But none of those results, none of those attempts turned out to be successful, and that's what we will discuss in the next lecture. So I will stop here. Thank you.